Robustness from classification to contextual bandits. And this is based on joint work with some awesome collaborators, Sitan Chen, Freddie Kohler, and Morris Yao. So actually, before I begin, let me just start off by giving you the bird's eye view of what the main theme of this talk is. So in this talk, what we're going to do is we're going to revisit some of the classic problems in learning, and we're going to study them in new models for corruptions that are going to be a blend of worst case and average case analysis. So part of what I'll be doing is just giving you an invitation to these models, why they're interesting, why they're important, and show you how to design some new and exciting algorithms for some pretty basic problems. So let me start off at the beginning, and let's start off with non-robust learning. So the first part of this talk is going to be in the supervised learning model. And the usual way that we study this is in what's called the PAC learning model that was introduced by Les Valiant back in 1984. So I'll keep this thing simple, and the way that it works is that you're given samples which are XY pairs. You can think about X as being a high dimensional vector and Y as a label. Now, just to keep things simple, we'll think about the label as being either +1 or -1. And the distribution on the x's is arbitrary and unknown to the algorithm. Now, the important thing is in step 2, what's going to happen is that you assume something about how the labels are generated. So there's some known class of hypotheses, capital H, and there's some unknown hypothesis, little h, that lives in that class. And the assumption is that for every single one of your examples, there's a little h that fits the label perfectly. So just to give a simple example so that we're on the same page, one of the classic problems in computational learning theory is the problem of learning half spaces. So here your class is the class of all half spaces, and there's an unknown actual half space, and each time you get a sample, it's an x, and then the y label is just +1 if it's on one side of the half space, and it's minus on the other side. And the goal is not to learn h exactly, because that is impossible in some situations. Instead, what you want to do is you want to estimate h approximately, in the sense that you output some other hypothesis h prime from the class, which has the property that h and h prime are very close to each other, that a typical new point sampled from your distribution, they'll have the same label and they'll agree. So actually what PAC learning stands for is probably approximately correct. So you want an efficient algorithm, both from a computational complexity standpoint and also from a statistical standpoint about how many samples you need. And then the goal is, to find an H prime that works. So the main part of this talk will be about, pushing back on these models where we assume that there's a hypothesis that perfectly fits our data. And this takes us to the notion of noise. So what happens if there's no simple hypothesis that fits our data exactly? And actually, there are many different frameworks that you can use to study noise. So at one end of the spectrum, you can think about a nice average case model for noise. One of the popular ones in supervised learning is what's called the random classification noise model. And the way that this works is it's the same as the PAC learning model. You take a bunch of samples X, and then they're each labeled with a label according to some unknown hypothesis. But the catch is that before you see the actual label, what happens is that you flip each of the labels independently with some fixed probability, say 1/3. And now you're in this situation where there's no longer something simple like a half space that perfectly fits your data. Now, it turns out that assuming that the noise is stochastic, is random in this way, and is the same across all of the different data points and is independent, well, that's actually a fairly benign model for noise. And there are provable and computationally efficient algorithms for learning under these particular models of noise, like RCN. So there's an older algorithm of Blum et al., which I'll talk a little bit more about later. Now, in many situations, assuming that the noise is random is just not an appropriate assumption, because maybe that's too strong an assumption in its own right. So at the other end of the spectrum, you can take a worst case view on what noise is. And this is usually called agnostic learning. So you make no assumption whatsoever about the structure of the noise. The adversary can flip the labels completely arbitrarily. And your goal here is to find a hypothesis H prime that has approximately the best agreement in the class. So you're agnostic to the belief that there is a half space that fits your data well. But in the case where there is a half space that fits it really well, you want to find another half space that does pretty well also. Now, this would be great in principle if we could actually achieve it. But the big problem is that agnostic learning is generally computationally hard unless you make further assumptions. If you make assumptions about, for example, the distribution of the x's. So in particular, there's some beautiful work of Kalai et al. And Awasti et al. That does exactly this. So they design agnostic learning algorithms for half spaces that work under the assumption that the x's are Gaussian or sub-Gaussian. And there's work of Amit Danieli showing that the problem of agnostic learning without making any distributional assumptions is actually cryptographically hard. So the main question that I'd like to broach in the beginning part of this talk is, are there challenging noise models where we can provably learn with computationally efficient algorithms without making distributional assumptions on X? So this is where beyond worst case analysis comes in, is because we've talked about at one end of the spectrum, the average case models, the random classification noise. And at the other end, we've had these worst case noise models like agnostic learning. But the question is there something in between that's both richer than random classification noise and yet lends itself to provable guarantees? So in this talk, the main thing that I'll be interested in is what's called the Massart noise model, which I'm a huge fan of. In fact, I've only learned about it a few years ago. And I think it's just a really cool model, and there are a few ways of thinking about it. So one of the ways of thinking about Massart noise is that you still have the labels of each data point flipped independently, but the kicker is that this probability eta of x depends on the data point x. So in fact, the noise rate can vary arbitrarily across the domain as long as it's always bounded away from a half. So it's always at most this parameter eta. And actually, there are a few ways to think about this Massart noise model, both as embellishments of the standard random classification noise model and weakenings of the worst case agnostic learning models. So let's think about it a few different ways. So one interpretation of Massart noise is that you can think about taking samples from your random classification noise model where everything is flipped independently with the same probability. So the noise rate is eta and it's constant across the domain. But now something funny happens, which is that some points X, they have a lower noise rate. So what you do is you allow an adversary to unflip some of the labels to put them back to their correct label that they were to begin with. Now, this sounds a bit wild, but it turns out that this adversary, who's not really an adversary because they're reducing the noise across the domain, that can actually destroy the performance of a lot of algorithms that work under RCN. So approaches like that of Blum et al. Actually fail in this extension. So I think that gives you a little bit of a teaser that, even when you have algorithms that work under some models for noise, they might be brittle in their own ways to the particular model of noise that you're assuming. So Massart, in some sense, is a way to push back on those particular modeling assumptions you made and understand how sensitive your algorithm is to those particular choices. Now, another way to think about it, and I wrote this as sort of, because it's not literally the same as the Massart noise model, but actually everything that I'll tell you will work in this model too. So you can take it as another definition for Massart, is you can think about it as a twist on the adversarial noise model. So an adversary can still arbitrarily control some fraction of the data, but the catch is that they don't get to choose what fraction of the data. So an adversary can arbitrarily control some random eta fraction of the data. So they no longer get to concentrate their corruptions disproportionately in just one region of space, where the noise rate is much higher than a half, for example. And the main question that I'll be interested in for starters is, are there distribution independent algorithms for learning with Massart noise? And remember that here distribution independent means I don't want to make any assumptions about what the distribution on x's is. So there's some really nice recent work of Diaconis et al. That got me excited about this stuff and introduced me to the Massart noise model. So what they showed was that there's a polynomial time algorithm for improperly learning half spaces under the Massart noise model. And they get this error guarantee of eta plus epsilon. And they get this for any positive epsilon. So one of the things that I want to emphasize is that, what makes this algorithm improper is the fact that even though there's a half space that fits the data very well, they don't necessarily output a single half space. Instead, what they output is much more complex, because what the algorithm does is it cuts up space into a polynomial number of regions, and there's a potentially different half space on each one. So in fact, this is kind of a big bottleneck in actually running these algorithms, because it's a very large number of regions that you cut space into, or even to describe the hypothesis that you output. So one of the questions that I'll be interested in is there a proper learning algorithm, something that actually spits out a half space? And there are a lot of benefits to doing that, because it's much easier to interpret what your hypothesis is. And one of the other questions you can ask is it possible to improve this error guarantee? Instead of this upper bound of eta plus epsilon, where eta is the upper bound on the fraction of points the adversary can corrupt, maybe it's possible to actually reach or compete with the optimal agreement within the class of half spaces. So is it possible to get stronger error guarantees that compete with opt instead? So the results that I'll be telling you about in the first part of this talk is that there is a polynomial time algorithm for properly learning half spaces under Massart noise. It gets the same kind of error guarantees, eta plus epsilon. And actually, maybe the most exciting thing about this algorithm is that it's really based on a very simple idea. So what we do is we give a general framework for how to design robust algorithms that are robust to Massart noise. That's based on finding an equilibrium for some exponentially large zero-sum game. So this paradigm of designing robust algorithms through playing games against an adversary gives us a lot of other results, as something else that comes out of the framework with some additional work. So we can do other things like design efficient algorithms for learning other kinds of models still under Massart noise, things like generalized linear models, which includes, for example, things like noisy logistic regression as a special case. So here we all know that we can solve logistic regression. It's a convex optimization problem. But it turns out that if you assume your labels come from this kind of generalized linear model that describes the law of the label y condition on x, then the same types of strange things happen that, if you reduce the noise in some way across the domain, that can actually destroy the performance of those convex optimization-based approaches. Instead, we give a way of rescuing their guarantees by building some kind of wrapper based on zero-sum games around them. So I won't say too much about the extensions to other kinds of models like generalized linear models. But one more thing that I want to mention is that we find some connections between learning under Massart noise and something else that Valiant introduced called evolvability. And what this allows us to do is it allows us to take some of the lower bounds that were proven in the evolvability literature and turn them into lower bounds against learning under Massart noise. So one of the things that we show is we show a lower bound in the form of statistical query lower bounds that are super polynomial for learning under Massart noise and getting error that's opt plus epsilon. So we give fairly strong evidence that you can't actually improve the guarantees all the way down to this optimal agreement. And through this connection, we can actually go the other direction and get some new distribution-dependent evolutionary algorithms that are resilient to drift from this connection between the two. So I won't be saying too much about that, but what I want to do now is I want to roll up my sleeves and talk about what is this zero-sum game, what is this framework? Because one of the neat things is that I'll not only be able to describe the framework in full, but I'll be able to give you basically the entire proof of an algorithm for learning under Massart noise. So the first thing that I want to do is I want to give you a little bit of a review about the notion of convex surrogates. So let's talk about loss functions even before we go there. So, usually what we care about is what's called the 0-1 loss. And I'm going to make my life easy. So when I think about a half space, I'll think about half spaces that go through the origin. So there's no longer going to be this offset B. We're just going to ignore it, and you can deal with that. It's not hard. And, if I think about having some hypothesis W, that's just the direction that's normal to my half space that goes through the origin. Well, I can take a sample, which is an XY pair, and I can take the inner product between W and X, and I can multiply it by -y. So this will give me some real value. And if you remember, what I want is I want my hypothesis W to have the property that the sign of the inner product between W and X matches the label Y. So if I've done things correctly, then the output for my hypothesis should be something that's negative. So it'll land on the other side of the Y-axis. And the 0-1 loss has no penalty because you're getting that label correct. Now, on the other side, that's when you've got the label wrong. It's positive because the label does not agree with the output of your hypothesis, and you're going to incur 1 loss. So that's the 0-1 loss. So when we talk about things like getting optimal agreement, what we really want to do is we want to solve an optimization problem over this loss function. I give you a bunch of data in the form of XY pairs, and I want to find the W that has smallest possible 0-1 loss. Now there's a big problem, which is that, this purple function that I've drawn here, it's clearly not convex. So the optimization problem that I get out is also non-convex. So one of the standard things that people do in computational learning theory is they relax a non-convex loss to a convex one. And they prove that, optimizing the convex loss is good enough. So one of the standard ways that you can do this is you can replace the 0-1 loss with what's called the Relu loss or the hinge loss. So it looks exactly like I've drawn. And the important thing is that this blue curve is now convex. So it's a convex function. So as a function of W, it's also a convex optimization problem. And the key point is that getting the hinge loss to be 0 is the same exact thing as getting the 0-1 loss to be 0. So now you have a convex optimization problem that can be used to answer questions like, is there a half space that fits my data perfectly? Now, of course, we're interested in the situation where there's noise. And in that situation, using this Relu is not a great idea. Instead, one of the things that people do is they use something called the Leaky Relu, which there's a parameter lambda, and basically you change the slope by lambda on each side. And I'll tell you more about the Leaky Relu in a few minutes. But the important thing about the Leaky Relu, I'll just assert it as a proposition for now, is that if you choose this parameter lambda correctly, how much you're changing the slope, then if you do it right, well, not only is it a convex loss, but what you can show is that minimizing it solves the learning under RCN problem. So basically what happens is that if you have some third probability of flipping the label of a data point, well, that's just going to reflect the data point over the y-axis because you're flipping the label. And what happens is if you choose this lambda parameter correctly, you can balance the loss of, getting some penalty for not agreeing with the label for the benefit of actually getting the correct label. So if you choose lambda as a function of eta, you just have to solve a convex optimization problem in order to solve this half space learning problem under RCN. Now, the important thing that I care about is, what happens when you have varying noise rates, like the Massart noise model. So let me tell you about our general framework for designing provable algorithms for learning half spaces under Massart noise. So it's going to look very, very similar to, the picture that I described earlier. So you're still going to have this Leaky Relu function that takes as an input this argument, which is minus y times the inner product between w and x. That part's no different. And on the outside, this min player is still going to be looking for a direction w that minimizes the expected loss, which is a convex function. The only difference is that now we're going to inject some adversary who is allowed to reweight the distribution. So this max player is allowed to say, hey, I only care about points X that land in this region, and I want to care about the conditional loss of the points that land there. I see that there's a question in the chat. So the question is, what's the intuition behind using this hinge loss instead of something more symmetric like a logistic curve? That's a good question. So yeah, I think there are actually multiple loss functions that you can choose for this. So, I think the main point is just that the Leaky Relu loss does work because it sort of balances. If you think about fixing X and then deciding whether you're going to add noise, it balances the loss that you incur when the label gets flipped and you end up on the wrong side versus the gain that you get if you don't flip the label. So it's not that other convex surrogates don't work. It's just that this is a pretty good convex surrogate to work with. Happy to take any more questions too. So in any case, this is the game. So please, ask me any questions about this game if it doesn't make sense. But, the thing that I want to tell you is that, the intuition for this is that if you think about in the Massart noise model, there is some true half space, W star. And the point is that this half space, W star, it not only does well according to the Leaky Relu loss on average over the entire distribution, but that's true even if you restrict to some portions of the distribution, because this hypothesis does well over all of space. There's no point in space where it has higher expected error than eta, because eta is an upper bound on the flip probability everywhere. So that's the intuition here, is that the true half space W star would be a good strategy for the min player, because if they play it, the max player can't find any region in space where they're doing badly. So that's the claim that I'll just assert, is that the optimal solution in this two-player zero-sum game for the min player is actually the direction W star, the planted true half space. Now, unfortunately, this zero-sum game is just completely intractable from every way that you look at it, right? So it's a zero-sum game, that's good. But, how big are the strategy spaces? So the min player is optimizing over the unit ball. That's pretty big. There are a lot of choices there. The max player is optimizing over all reweightings of the distribution. In fact, not only is the best response problem of choosing the best response from one of the player's perspectives computationally hard, in fact, it turns out that this framework is even statistically hard to reason about. Who's to say, when I really care about the loss function as being the expected loss, that I can take a polynomial number of samples and estimate the expected loss? That's very tricky because the max player has so many choices of strategies. So this is a good idea, but it's kind of dead in the water right now, because even if finding an equilibrium would solve our learning problem, there's no real sense algorithmically or statistically in which we can meaningfully find the equilibrium of this game. But it turns out that there's a way to change the game to make it algorithmically and statistically tractable, where you can show that finding an equilibrium is good enough as well for solving the learning problem. So here it's going to look very similar. We still have this Leaky Relu loss. We have this min player who's looking for a direction W, that's the normal vector to the half space. And now the max player, instead of being allowed to look at arbitrary reweightings of the distribution, he's only allowed to look at reweightings that focus in on a particular slab. And by that, I mean, when we look at the current hypothesis W, well, you take all of your data points and you project them onto the direction W. And then what the max player is allowed to do is he's allowed to choose some slab that you're only going to look at points in the distribution which land between -r and r. So what we show is that any approximate equilibrium to this game necessarily corresponds to a hypothesis with low error for the learning problem. So are there any questions about the zero-sum game framework before I dive into how to analyze it? Nope. Okay. So the cool thing about this framework, I mean, the thing that you should be surprised by is, why did the equilibrium of this game have anything to do with solving the learning problem that we started off with? And the fun thing is that I'll be able to give you basically a complete analysis of it, just in a couple slides. So let me introduce one more basic notion from computational learning theory, which is the notion of margin. So margin is the smallest distance of any example from the true decision boundary. So remember that when we have the 0-1 loss, well, if there's a half space that perfectly fits our data, then all of our data points land on the negative side of the x-axis. And the margin is just, the distance from, the decision boundary where it changes from the output of the label for your hypothesis. So it's really just the distance from, the y-axis or 2 times that, depending on how you measure it. And let me tell you, it'll boil down to just 2 key lemmas. One of them is very simple. In fact, it was already in the earlier work. So what I claim is that in the Massart noise model, if you choose this Leaky Relu parameter lambda to be larger, or at least as large as the parameter eta, and the distribution on x's has this margin gamma, then what I can do is I can show that the Leaky Relu loss for the true hypothesis W star, the true half space, is negative. And the value that I get on the right-hand side depends on the margin and lambda's relationship to the error of that true hypothesis W star. So this says that the true hypothesis W star does very well according to the Leaky Relu loss because it has negative loss. So this is a very simple lemma to prove. I'll prove it just in one slide. And actually, first thing I should do is I should make good on defining what the Leaky Relu loss is precisely. So, if you think about the 0-1 loss, then it really corresponds to the case where lambda is equal to 0. Because, what happens is you have this indicator function of whether or not your hypothesis gets the label correct. And then you multiply by the absolute value of the inner product between W and X. So, if you get the label right, then you output 0. And on the other side, if you get the label wrong, then you output this, your loss has slope 1. And the Leaky Relu loss just subtracts lambda from the indicator function. So that's the definition of the Leaky Relu loss. And it's convex because you saw me draw it. So what we do is, the key to the proof is just subconditioning. So we take a sample from our model, and then we condition on X. And then we look at the remaining randomness on the chance that we flip the label Y, which remember, the chance that we flip the label Y is this parameter eta of X. So if we write out the Leaky Relu loss, well, the indicator function just becomes the probability that we flip the label. And this value is at most, it's eta of X, and it's at most eta. And by assumption, it's at most lambda, because that was an assumption in the lemma. And then because the margin is at least gamma, this absolute value term, is also at least gamma. So we get exactly this upper bound that I promised you, that we get something that is a negative upper bound, and it depends on the margin of the underlying distribution. So that's it. We're down one lemma. We only have one lemma to go before we can analyze the simple zero-sum game. And one of the key takeaways that I want to emphasize just about this lemma, it's short and sweet. So this lemma tells us that the true direction achieves small loss. But let's think about this in the context of the zero-sum game that we had to begin with. And what I claim is that in the zero-sum game, even if the max player is allowed to focus in on some region of the domain, well, this lemma is still true, even if we look at the conditional distribution on that region. All we used was the fact that at every data point across the entire domain, doesn't matter how we restrict the distribution, its flip probability of adding noise is at most eta of x. So let me tell you the second lemma. This one's a little bit more involved, but what I claim is that in the Massart noise model, imagine that you have a hypothesis W and its error is large. And by error, I mean, what fraction of the data does it get wrong? So let's suppose that the current hypothesis W has the property that its error is at least some parameter lambda. And remember, lambda is at least this value eta. Then what I claim is that there is some slab. So there's some choice of R along, for the slab along the direction W, so that the Leaky Relu loss of W when you restrict to that slab is non-negative. So this lemma would actually, be great. This would, tell us we're done, that any equilibrium is good enough for solving our learning problem, because what it says is that if the current direction W does not achieve small enough error, so its error is at least lambda and is not smaller than eta like we want, then it says that the max player can do well in the game. They can actually make our loss restricted to the slab non-negative, even though from the first lemma, we know that we're trying to get the loss to be negative. And so what this means is that, in this game, if you have a strategy for the min player that does well, no matter how the max player responds, that's equivalent to achieving small error on your learning problem. So this would tell us exactly what we're after, that any equilibrium in this game is good enough for our purposes for solving the learning problem. So the proof of this lemma turns out to not be so bad. So what we're going to do is we're going to assume, for the sake of contradiction, that there is no slab. So what we're assuming is that the current hypothesis W has large error, and there is no choice of a slab that makes the Leaky Relu loss non-negative. So what we can do is we can just write out literally what that condition means, is that means for every choice of R, because that's how our slab is defined, that expression we had before, which defined the Leaky Relu loss, well, that by assumption, let's say, is negative, right? We're going to assume that it's negative for all R, and we're going to prove this contradiction that our error cannot actually be large. And so all I've done here is I put in the Leaky Relu loss, and then I have this indicator function that defines the slab, which is just whether the absolute value of the inner product between W and X is at most R. And now we're just going to use a very simple identity. We all know that, for any positive X, X is equal to the integral from 0 to infinity of the indicator function of whether Y is less than X. And what I can do is I can use this identity to absorb this absolute value of W inner product with X. So what I'll do is I'll absorb it into an integral where now I integrate over some other parameter S, only up to this threshold of the absolute value of the inner product between W and X. So, this is just a rewriting of the expression, but now the thing that we're conditioning on, this indicator function, is no longer a slab. What it really is it's an annulus. Now, completing the argument, well, if we know that the integral over S is negative, then it implies that there is a choice of S, so that the argument inside the integral is -2. So it says that for every R, there's a choice of S of R, so that the thing that was sitting inside, the Leaky Relu loss times the indicator function of this annulus is strictly negative. And now we're in good shape because, what we can do is this indicator function for this annulus, well, if we divide by the appropriate probability, this will turn into a conditional probability, and the lambda can be pulled out on the other side. So rearranging this inequality tells us that this lambda parameter from our Leaky Relu is an upper bound on the conditional probability that we get the wrong label for our hypothesis, where we condition on the data living in the annulus. And now we're actually done, because what we can do is we can chain together a bunch of these regions. We start off with some threshold R, and then this argument tells us there is an S of R, so that this contribution of the conditional error is less than lambda. And that becomes our next R, and there's a new S of R. And when we chain all these regions together and average them in the right way, we'll get the overall error of our hypothesis. And because we're just averaging both sides of these inequalities, we'll get that lambda is actually strictly larger than the error of our hypothesis. So this contradicts the assumption that we started off with, that W has large error. So that's it. That analyzed the equilibrium. It told us that finding a good equilibrium in this game is enough to solve our learning problem. And actually, there is one more question I have to address, which is, how can we find an approximate equilibrium algorithmically? So here, online convex optimization is going to come to the rescue. So there'll be a simple iterative algorithm for converging to an approximate equilibrium, which, this algorithm is going to be based on the key idea that not only is the Leaky Relu loss convex, but same goes when we restrict it to a slab. So how does this algorithm work? We initialize some initial hypothesis W. It can be any vector in the unit ball. And then what's going to happen is that the max player is going to best respond. So given the current hypothesis W, the max player chooses a threshold R star that maximizes the Leaky Relu loss restricted to the slab. Now, if that loss itself is pretty small, it's at most epsilon, the best that the max player can mess things up is to make the loss in the game be at most epsilon. Well, then, by the second lemma, we know that we're good. That, the fact that the Leaky Relu loss is small and there's no slab where it's large means that the current estimate W must have low error for our original learning problem, and we can finish. But the key question is, what happens when the max player finds a threshold R star, which defines a slab so that the loss is large, is very positive? Now convexity is going to come and save us, because I mentioned that this Leaky Relu loss, even when you restrict to a slab, is convex. So what should you do to improve your current estimate is you should just take the gradient of this loss and take a step in the direction opposite to the gradient and project back to the unit ball, because that's the space of hypotheses you care about. So it turns out that you can use a lot of standard tools from online convex optimization to show that this simple algorithm actually provably finds an approximate equilibrium, and hence provably solves this Massart learning problem. And the intuition is that, this is online convex optimization, and online gradient descent are low regret algorithms. And we know that there is a choice for the min player, namely W star, that's very good. So if this game goes on too long, then the min player is actually incurring a lot of regret, which violates some of the bounds that people know in this literature. So I think this is a neat way of both combining, robustness considerations, computational complexity issues about how do you design efficient algorithms, with some ideas from, game theory and online convex optimization. But, what I want to do now is I want to bring in even one more idea. I want to tell you some empirical ways that these algorithms are very good, with some connections to fairness. And there's another question in the chat, which is W star the half space after the noisy label is determined? So W star is the true half space, which fits the labels before you add the Massart noise. So there's one true W star, And that W star would be good, both for the learning problem, because it would achieve error at most eta. And also what we argued about before was that it would be a good strategy for the min player, because the max player can't find any region in space where that hypothesis does badly. So it's really a planted part of the generative model in this setting. All right, so in the time that remains, oh, there's one more question. Does the algorithm depend on the flipping rate function eta of x? So that's a great question. So it actually does not depend on the flipping rate function eta of x. What it depends on is having an upper bound eta for the eta of x. So in fact, the only thing that I need to set in my algorithm is that eta then determines, a constraint on lambda, which is the thing that actually goes into my Leaky Relu loss. But otherwise, we assume nothing about, how the noise rate varies across the distribution. It's, the algorithm is totally oblivious to that. Great questions. Any more questions? And do you also need to have an efficient algorithm for finding R star? Sorry, I should have said this. See, R star you can find just by grid search because it's a one-dimensional problem. So once you've chosen the hypothesis W, then you just have, a discrete set of choices for, how to choose the threshold R star. And what you can show, in the actual paper, we analyze, even if you don't find the optimal R star, you find something that's close, that's still good enough. And there's a question, which is, how is this different from RCN? So remember that RCN, the noise rate is the same across the entire distribution. Here, it actually varies arbitrarily across the distribution. It's just that there's an upper bound. In fact, that's a good segue, which is maybe we should study this empirically. So what I claim is that algorithms that work under RCN fail spectacularly once you allow the noise rate to vary. And that's true even if the way that you're making the noise rate vary is actually reducing the noise in some parts of your distribution. So that may sound kind of surprising and alarming, but it's true. So let's see it empirically. So, let's ask this qualitative question, which is, when is this noise model useful, right? Which is, I think, what the question was anyways getting at. So one thing that, I'd like to tell you a little bit about is, so first, there's the standard data set that a lot of people in fairness use. It's a very simple data set. There are more complicated ones too, but it's the UCI adults data set. So the way that this data set works is that there are about 50,000 individuals, each of whom you think of as a data point. And each of them have 14 attributes, 14 possible attributes. So you think about, things like their marital status, their education level, their ethnicity, their gender. These are all different attributes, and each of these people are just a 14-dimensional vector. And your goal is to predict whether their yearly income is above or below 50K. So what we're going to do is a little bit weird here, which is we're going to take this data set and we're going to inject our own noise just to understand, how robust or brittle some of the standard algorithms that we know and love really are. And one of the motivations for thinking about these kinds of experiments is that there's actually tons of social science literature, which are empirical studies about when and why the noise level varies across different demographic groups. So for example, when you do health surveys, actually it's well known that your noise rate varies in pretty extreme ways across different demographic groups, because some people don't have English as a first language, so there's a lot of noise in the responses. And some people just don't genuinely trust the medical systems which they're replying to. So they add a lot more noise, or you get more noisy answers from those people. So what we did was a little bit strange, which is we took this UCI adults data set. We took, some target group, which is a small minority group in this data set, and we added noise outside the target demographic group. And then we ran off-the-shelf algorithms whose goal was to maximize the overall accuracy. And what we did was we asked how much adding noise outside a target group affects your accuracy in that target group. And something, pretty shocking happened. So first, let's do the plot on the left. Filtertron is the algorithm that I was describing. It's something that's designed through the zero-sum game framework to tolerate heterogeneous noise rates across the domain. And without even knowing what that heterogeneous noise rate is or how it depends on different demographic groups. And you can try things like off-the-shelf logistic regression, or using an algorithm that works under RCN for learning half spaces. And as you add more and more noise outside the target demographic group, if you look at the overall accuracy, nothing surprising happens here. The larger your noise rate, the worse your overall accuracy. Makes sense. That's true for all of these three algorithms. But now when you look at the target group specifically, where I emphasize no noise has been added, things like RCN and logistic regression do catastrophically bad. Because when you add just 20% noise to the rest of the population, they say that within this target demographic group, there is not a single person who's above 50K per year for income. So they interpret all of the positive examples in that target demographic group as being noise, just because the rest of the distribution has roughly that noise rate too, and they're designed to optimize the overall accuracy. And you can see that our algorithm has no such trade-off, basically. So it remains pretty flat across that target demographic group, even though it gets about the same overall accuracy. This is true for other target demographic groups. We tried a bunch of things in the paper. So, one of the things I'm excited about is this connection between robustness and fairness. Because what I claim is that, many natural algorithms, even just empirically, without getting into normative definitions of what fairness is, even empirically, things that we know and love, like logistic regression, they have this bizarre property that they amplify certain types of biases in the data, because they're not designed to work for heterogeneous noise rates. But in contrast, some of the algorithms that we're designing here, which are deliberately designed to be robust to varying noise rates across the domain, well, they turn out to be more fair exactly because they're expecting some level of heterogeneity. So, in most of my time, I spend time thinking about designing provably robust algorithms with, which are computationally efficient. But I'm also very excited about using these kinds of tools to enable, machine learning guarantees that you can trust more in a wide variety of settings, or being building blocks of some more complicated machine learning systems. So I have very, very, very little time. So, I guess I kind of expected that, but I'll tell you a little bit, going forward about some of the other results we have that are of a similar spirit. They just, take it outside of the supervised learning paradigm and into online learning. So in online learning, we could also take a very basic and fundamental problem, which is online linear regression. And there your goal is to solve a sequence of linear prediction problems. So what happens is in each time step, you observe a covariate xt. Think of it as a high dimensional vector. And then what happens is you want to predict the response. Now, the true response that you observe looks like the inner product between W star and xt. So W star is the true regressor. And then you add some additive noise that's, Gaussian or sub-Gaussian. And your goal is to predict this response yt. And the loss that you incur depends on the squared error between your prediction and the true response that you observe. So the classic solution is something very simple, again, based on convex optimization, which is something called online gradient descent. So you can solve this problem very well, even without assuming anything about the xt's. They might not even be coming from a distribution because they could be adversarially chosen according to some adversarial sequence. And nevertheless, you can get strong guarantees. But, the same way I'd like to ask, what happens if we don't have this additive stochastic noise? What if some of the responses are adversarially corrupted? Along the lines of, for example, the Huber contamination model. This actually sounds very similar to Massart noise. The idea is what happens if a random eta fraction of the responses are arbitrarily corrupted. You can't say anything about what happens with those responses. So it turns out that online gradient descent is still okay. Because, first what you can do is you can look at the average mean squared error. But actually, if some of the responses are arbitrarily corrupted, you can't really look at the difference between your prediction and the thing you observe. You should look at the clean error, namely, the difference between your estimate and what the true estimate would have been without the corruptions. And what you can show is that if all of your covariates xt have Euclidean norm at most r, and your regressor w star has norm at most 1, then what you can show is that the clean average mean squared error you can obtain is at most eta, this corruption rate, times r squared. So that sounds pretty good until you realize that it's actually extremely far from optimal. Because the optimal, lower bound, you can show information theoretically, is that the clean average MSE, you can only show a lower bound that it should be at least eta squared times the variance of the stochastic noise. So it actually should have nothing to do with the dynamic range of the covariates at all. So the way to think about this pictorially is, when the dynamic range and the variance are close to each other, then the cone of lines that achieve nearly optimal mean squared error, at least within constant factors, is very wide. So in fact, when you add corruptions to this, they never really pull you that far outside the cone. And that's why online gradient descent still works. The trouble is when the range is much larger than the variance, then the cone becomes very narrow. And those same types of corruptions can push you very, very far away from optimality. So what we showed was that there's a simple and practical algorithm that gets the nearly optimal mean squared error in this online linear regression model. So not making any assumptions about the x's coming from a distribution. They're chosen in an online fashion in this very strong Hilbert contamination model. And it turns out our algorithm is actually a simple twist on a classic algorithm, the same way that it was before in the Massart situation. I'll mention, in case you're curious, you can show that classic heuristics like Hilbert regression, they provably fail and they incur this, R dependence, which is unnecessary. There are other works that, make distributional assumptions that the x's are, Gaussian or something else like that. But instead, what our algorithm is, we take the simple least trimmed squares estimator going back to Rousseau, where what you do is you start off with S as the set of all data points. You let W hat be the output of running ordinary least squares. And then you throw away all but the points whose residuals are the smallest. And then you iterate, you go back and forth until convergence. This heuristic is widely used, but it doesn't work in a worst case sense. There are ways with Hilbert contamination that you can badly mess this up. But our twist is very simple, is instead of looking at an arbitrary set of points with small residuals, we look for sets that are spectrally well spread out, in the sense that their covariance is approximately the same as the covariance of the original set of data points. And that's exactly how you can get these strong provable guarantees for online regression in this Hilbert contamination model. So I'll tell you that there's some pretty neat experiments we can do to compare, our algorithms, where we get orders of magnitude improvement in the clean MSE. In fact, you can even, extend these things to what's called linear contextual bandits that have a lot of applications in e-commerce, collaborative filtering, mobile health. And we can get the same types of guarantees just because linear contextual bandits are very related to the online linear regression problem. So I'll basically stop there with the technical portion, and I'll just conclude with, some parting philosophical thoughts. So I've spent a bunch of time, recently thinking about robustness and, whether it's in tension with computational efficiency. Because a lot of the simple models we start off with in learning, they're not models that we literally believe. So there's this need for trying to stress test our algorithmic guarantees and understand whether they hold up to different sorts of noise. But there's not any one model of robustness that's really the one size fits all. It's, really a spectrum. because, even between average case models like RCN and worst case models like agnostic, sometimes there are interesting compromises in between. So it's not just about handling more powerful adversaries, but finding the right compromises that avoid some of the computational intractability assumptions. And one of the things that I'm really interested in these days are there real world applications where having these building blocks of provably robust estimators that are more robust than some of the other standard algorithms that are near and dear to our hearts, well, can that improve things in practice? So I'll stop there, and yeah, thanks for listening. Happy to take any additional questions you might have.
All right, thanks very much. First, I'll just suggest we thank the speaker by clapping a little bit or something. And yeah, any questions? Oh, I'll stop the recording.